All right, so today's first topic is the demodulation of single sideband signals. The first idea is coherent demodulation. Coherent demodulation means that you have the right carrier at the demodulator. How do you obtain that? You usually obtain it using a phase lock loop. Okay? Suppose you have the carrier at the correct frequency with a phase mismatch, a phase offset. Let's see the result of demodulation. The demodulation process is similar to the demodulation of double sideband, where you mix the incoming modulated signal, the received signal, with a cosine, and then low pass filter the result. Now, the incoming signal, if it is the same as the transmitted signal, it looks like m of t cosine 2 pi fct plus or minus m hat of t sine 2 pi fct. What is m hat here? Right, m hat is the Hilbert transform of the message signal. Now, this could be plus or minus. In the case it's minus, it corresponds to upper sideband. Great. In the case it's plus, it corresponds to the lower sideband modulated signal. Now, we're multiplying with cosine, right? Let's carry out the multiplication. Let's just, maybe we can all try to do it together. M of t cosine 2 pi fct minus, let's pick the minus, or we can keep the plus alongside with the minus. Hilbert sine 2 pi fct multiplied by twice cosine 2 pi fct plus pi. Now we have from the first term, I will just bring it up here, bring it down here. The twice m of t times cosine 2 pi fct cosine 2 pi fct plus phi. Cosine times cosine is 1/2 cosine of the sum 4 pi fct plus phi plus cosine of the difference. Okay. And then from the second multiplication, we have twice m hat cosine times sine, which is 1/2 cosine times sine is sine of the sum plus the sine of the difference, sine minus phi. So this is a, oops, this is a minus. Okay, so now after filtering out, the 4 pi fct terms will disappear, and we will have m of t cosine phi plus or minus m hat of t sine phi. Notice that because of this negative sign here, the plus and minus have switched places. And also notice that if phi is close to 0, then the second term is negligible, which would mean we would have perfect reconstruction. Okay, so if there's no phase, if there's no phase offset, we will have perfect reconstruction. Any questions so far? All right. So now, if there is a phase offset, non-zero phase offset, in the upper side, so basically for now, suppose that the original SSB signal was an upper sideband. So assume upper sideband to start with. okay, then the received, the demodulated signal is m of t cosine phi plus m hat of t sine phi, but this thing itself looks like a what? M of t cosine something plus m Hilbert sine something. That itself looks like a LSB, right? So it's like, so that's, we can use the fact that it looks like an LSB, SSB signal to understand it better, but let's first analyze it in the frequency domain. Y of f is m of f cosine phi minus j signum of f, m of f sine phi. What is the j signal coming from? It's coming from the Hilbert transform. Okay, now collect the terms together. Just factor out m of f, and we have cosine phi minus j sigma f sine phi, which basically corresponds to e to the negative j phi m of f for positive frequencies, and e to the j phi m of f for negative frequencies. So this is like taking m of f and passing it through the filter h of f, where h of f is an ideal phase shifter. Ideal phase shifter by theta, because for positive frequencies, it adds no magnitude, it adds a negative phase, and for negative frequencies, it adds a positive phase. So this is some kind of distortion, but in the case of voice transmission, it is not an important distortion. But in general, it is distortion. Now, if there was a frequency offset, well, we can always model a frequency offset by a time varying phase, right? So if the frequency offset is delta f, the phase is going to be 2 pi delta ft in time. Okay, then our recovered signal, our received signal, if the original modulated signal was upper sideband, our recovered signal will look like this. Now, this thing, because there's a minus here, this is itself an upper sideband signal, okay? And what it looks like is a translation, not really a translation. First it's translated and then filtered by the Hilbert transform filter, remember? So basically, it is an upper sideband signal at delta f. So you can see the distortion is in terms of shifting the frequency content, which causes, in the case of sound, higher pitched sound. Okay, so this is annoying in the case of voice. Okay, the phase error is not annoying. Okay, so how do we detect SSB using an envelope detector? If we add a carrier to SSB, we should be able to recover it using an envelope detector, similarly with conventional AM. Okay, but the analysis is a little bit different, so let's go through that. Okay, so suppose a carrier at FC is somehow available at the receiver. It can be locally generated and added. Okay, that is possible, but it sort of beats the purpose, right? If we want to use an envelope detector to detect the signal, well, and if we had a carrier, I mean, we could have just used coherent detection in the first place. So this is sort of like an imaginary case. The actual use of using an envelope detector if the carrier is sent alongside the transmitted signal. Okay, so in that case, suppose S of t and the cosine are added, I'm sorry, multiplied. This is a typo. Oh, no, added, I'm sorry. S of t and the cosine are added. Okay. And the result is passed through an envelope detector. What do we get? Let's see. So we have the carrier and the lower sideband modulated signal. So collect the cosine terms together. And we have a cosine and a sine. We can always combine these together from trigonometry using and bring it to a form of cosine 2 pi fct minus some angle, which we will compute, multiplied by some amplitude that we will compute. You know very well that in this case, the amplitude is the square root of the first term squared plus the second term squared. And the angle is the arctangent of the ratio of m hat to a plus m. Okay, now if you don't remember this, remember it as homework. You got to know how to do this. Okay. Now here is the point at which we need to make some approximations, because the envelope detector is not going to work under all conditions, as you can imagine from conventional AM. Okay, in order for envelope detection to work, we need the envelope to really resemble the modulated signal, and that is not going to be the case in all conditions. So suppose the carrier is large enough, okay, then the signal magnitude, amplitude that is much less than the carrier. Under that condition, we can make the simplification here in E of t that the first term dominates, the first term in this square root dominates the square root. So then we can sort of get it out of the square root, okay? And resulting in E of t being approximately a plus m of t. Okay, so this is provided that the carrier is large enough, which also puts an upper limit on the power efficiency. Okay, so then that's that. Basically, that means what did we achieve? We achieved that the envelope is almost equal to the message signal m of t plus a constant. So we have detected the message. Okay, so that would be sort of a cheap and inefficient way of detecting SSB. All right, any questions? Now, here is the big idea for today. This is the most important thing you will learn today, and probably maybe in all of this course. It is quadrature amplitude modulation. Because if any of you have dealt with any physical air communications so far in your summer practice or in reading a book or an article, you have seen that we use forms of quadrature amplitude modulation a lot in digital communication as well. So what is quadrature amplitude modulation? We'll make the step to quadrature amplitude modulation from our understanding of SSB. In SSB, we saw that we can combine the signal m of t and its Hilbert transform by multiplying each with quadrature carriers. Quadrature means they are at 90 degrees to each other. One is a cosine, the other is a sine. Now, you know that the cosine and sine are orthogonal, right? Right, they're orthogonal. Basically, their inner product is 0. Now, the idea is, if we are taking m of t and m half of t and multiplying by orthogonal carriers, who says we need to use Hilbert transform pairs? We could pick 2 independent messages and multiply them with the quadrature carriers. So have m1 of t, one message, and m2 of t, another independent message, and use cosine as carrier for the first one and sine as the carrier for the second one. They will not mix because the cosine and the sine are orthogonal, and we will now see when we try to demodulate that they will not mix. Now, this is, if you think about it, the first term, this first term, what does it look like? Double sideband suppressed carrier, right? The second term also looks like double sideband suppressed carrier. Think of the sine as a cosine that just has a phase of 90 degrees. Okay, so there are 2 double sideband suppressed carrier overlapping on the same frequency band. In time domain, we will be able to totally recover them separately. You will see it now mathematically. So we are transmitting 2 double sideband signals on the same frequency band. What was our reason for doing SSB in the first place? Bandwidth efficiency. Okay, we were using, so in double sideband, we use 2W to transmit a message of bandwidth W. In SSB, we use W to transmit a message of bandwidth W. In this one, we are using 2W, but we are transmitting 2 signals, independent signals of bandwidth W each. So we're using 2W to send twice the amount of information. So the bandwidth efficiency is exactly the same as SSP. Yes, please. Yeah, that's also possible. You could put 2 single sideband messages in different frequencies, which is frequency division multiplexing. We will talk about that later. Okay, but let's focus on this now. Quadrature AM, QAM, is essentially the default mode for many physical layers, because we often have the so-called in-phase branch and the quadrature branch. Today, you will go to the lab and have your first session with the RTL SDR. You will see it works like this. There's an in-phase branch and the quadrature branch. So another way to represent QAM would be using phasors. Okay. Now, since we're talking about, let me write it here again, m1 of t cosine 2 pi fct plus m2 of t sine 2 pi fct, I could always write this as the real part of some complex signal. The real part of a complex signal. Of course, I'm not going to be transmitting a complex signal, right? But I can always imagine that I'm transmitting the real part of a complex signal. This is a point at which a lot of people, if they don't think carefully, they end up getting lost. So that's why I repeated it. Now, I'm thinking of it as the real part of the complex signal. But then I will go ahead and kind of work on the complex signal as if there is such a signal. In the actual physical layer, there is no such signal, complex signal. But I will, I do not lose anything by working on that complex signal and then converting it to the real part. Okay. Now, from this point on, as you study communications, you will always be interested in complex signals. This is why. Okay, so good news or bad news, I don't know, but I'm giving you the news that we will be dealing with complex signals. Okay, now define a complex message then as mi of t minus j mq of t. A complex message is the combination of two independent messages, if you will. I mean, they do not need to be independent, but two messages such that mi of t is the in-phase component and mq of t is the quadrature component. You can map it to all kinds of communication, all kinds of modulation schemes. For example, in double sideband, mi of t would be positive and mq of t, mi of t is non-zero and mq of t is 0. In SSP, mi and mq are Hilbert transform pairs. In general, in QAM or in QAM, mi and mq are arbitrary signals. All right. Okay. So what is the system diagram? mi of t comes in here. mq of t goes in there to a modulator. And we have a cosine mixing with the in-phase branch. And we have a sine mixing with the quadrature branch. Of course, we need to generate the cosine only once. We can use a negative 90 degrees phase shift to obtain the sine. And then the two branches are added together to form the signal to be transmitted. Now, in the case that we're transmitting two independent messages, one of them with a Fourier transform that looks like a triangle, and another rounded Fourier transform shown here for description purposes, they will be overlapping in bandwidth. But this overlap is not a loss of information. As you will see now, we can demodulate them separately. How? Well, take the modulated signal and multiply with a cosine and multiply it by a sine separately and separately low pass filter the results. Let's see what happens. Now, y sub I of t is s of t times twice cosine 2 pi fct. But s of t was, remember, mi of t cosine minus mq of t sine, or plus mq of t sine, right? So when we multiply it by cosine, the result is this. When you low pass filter, what do you get? When you low pass filter, this is gone, this is gone. Wow, mi of t. Mi of t, the in-phase branch signal. And similarly, YQ here is MQ of T times these things, and these things are filtered out. And we have at the output of the quadrature branch of the receiver MQ of T. So we recovered MI and MQ perfectly. Okay, so that means that quadrature amplitude modulation works. The two signals that we put on the in-phase and quadrature branches do not mix. So through quadrature amplitude modulation, we are able to transmit two independent signals and double our double the amount of information that we're transmitting. It is easy to perform demodulation. So this is now the standard technique in the digital era, and you will see more of this in the course 436.